Hello there, Math 126 fans. This is going to be a lecture on 15.1 to replace in-class time. This is going to be an intro to the theory and the Riemann sums. At the end of this video, I will peek at the homework and give some tips. I probably will have a second video where I go into some detail on a few particular problems. So let's go. Let's get into this. 15.1 is the introduction to double integrals. And so rather than just jump right into the theory, I always like to do an example to give you a taste. This is what I do in class, a taste of what it's going to be about before we get into the theory and I get you all confused. So here we go. Usually what I do is I split the class in half. So if you're sitting on the left half of the people watching this video or the right half, you can just randomly pick a side. So as you're watching this video, I'd like you to compute one of these. The way we compute is we treat x like it's the variable, work from the inside out, and we treat y like it's a constant. Here you're going to treat y like it's the variable, and x is the constant. Okay, so hopefully you're trying one of those. You could pause it, you could compute it. You can see that I've actually switched the numbers. These numbers go with x. These numbers go with y, and this is called an iterated integral. Again, we'll talk about the theory in a second. I just think it's kind of nice to ease our way into it with an example. So the punchline is these two things are the same, and it turns out they represent the volume between the rectangle you get when you consider all the values where x is between 1 and 2, and all the y values you get when y is between 0 and 2. In fact, it's this rectangle you're seeing on the right of the screen. That rectangle is actually this. So I turned it so you couldn't see, but the surface, the blue thing there, this is just to get a taste of it, is this surface. I've chopped it off so you can just see it. That's 8xy squared. That's that thing. So what we're actually going to do is we're going to find the volume between these. That's what we're doing in this section. But it's not just about finding volumes, it's about measuring something over a region, and that's what we're going to be doing in the next few sections. Okay, so it turns out this is indeed the volume of that solid you're seeing on the screen, and this is also the volume. These are both the same thing. One does it in terms of x first, one does it in terms of y first. Okay, let's just talk about the mechanics of computing. So you're going to do the integral from 0 to 2 dy, and you're going to integrate as if x is your only variable and everything else is a constant. So it's going to feel like partial derivatives. If you integrate x, so the other things are constants, let's just copy them down. And if you integrate just the x, you're going to get 1/2 x squared with these constants in front of it. And then you're going to evaluate that from x equals 1 to x equals 2. Now when you're done doing that, you're going to get a number here. So let's compute it. Let's see what we get. We get the integral from 0 to 2. The 1/2 and the 8 will make 4. Y squared. I tend to like to factor when I'm doing this because I know this is part of all of it. So this is going to be 2 squared minus 1 squared. I imagine if we were in class, students would say, where did the 1/2 go? Well, I multiplied it times the 8. That's it. So that's regular integration for one variable. I think this is 4 minus 1, which is 3. And so that's 4 times 3. I would just write that all out in front as 12. What I'm writing here actually represents something, but let's just keep going. So then you integrate again. Now it's just a one variable integral. It's 12 over 3 y to the third from 0 to 2. And when I do that, it's 4, 2 cubed minus 0 cubed. And quite a bit of the homework is just, like I said, quick integrals like that. So this is 8 times 4, it's 32. Let's say we're in feet, so this would be cubic feet. That's the volume of that thing. I think the height of it is at the peak close to 50, but it's much lower on the other side. Again, it's 1 by 2 on the bottom. So you could estimate whether you think the volume is reasonable. That's a nice thing to do. Okay, let's do it the other way. So go ahead and try and see what happens when you do it the other way. So treating y as if it's the variable, your first step in integration would be, we'll write all this out. The integral from 1 to 2, here's what you're going to get, 8 thirds x y to the third. The 8 and the x were coefficients. The y squared became 1/3 y to the third, 0 to 2. And students get mixed up in this notation. So the first few times you do this, it's kind of slow. You have to remember what you're plugging in here. Okay, so we're all done. It's going to be 8 thirds x. I think that's just times 8 because we're plugging in a 0. And so this is going to be 64 thirds, the integral from 1 to 2 of x dx. And then if we integrate that, it's 64 thirds, 1/2 x squared from 1 to 2. That's 32 thirds. You can see again how I like to simplify this part. And then it's going to be 2 squared minus 1 squared. And that's 32 thirds times 3, which is also 32. Ah, that's nice. That's the mechanics. So if you just wanted the mechanics of chapter 15, most questions will end that way. You can see in there most of the integration was quick. There will be some where you have to do substitution or by parts or something. But it shows that we have these two examples. So I like to start there just to show you this is really what you're going to be doing. Now, a few comments here. Get rid of a few things here. What we're actually doing is we're looking at slices in the following way. So the moment we fix x, which is what we're doing when we're in here, x is fixed, we are actually looking at a particular cross-section. So this expression, the 64 over 3x, actually represents the cross-sectional area. And I'll go back to this later here in this lecture, but it's that cross-sectional area. So this is just like when you did discs and washers back in 125. It's just the cross-sections are not discs and washers. So this thing in the middle represents the cross-sectional area at a given x value. It just doesn't have a nice pattern. And when we're doing it the other way, we're just switching and we're saying, okay, now I want to fix y, and we're going to go this way. And so it's actually not a new method, but we do have these two possible ways to do it. Okay, that's the visual. So the mechanics is you're just going to integrate the inside, then integrate the outside. The theory is that we're actually doing cross-sectional areas. All right, so let's talk about some notation stuff. So how do we make this more official? And I'll get rid of this picture for a second, and I'll explain. So we don't do a lot of Riemann sum theory like you would in Math 125 just for time. But let's say you can't integrate. Then what we do is we break up the region on the ground into subregions. So the thing you have to get used to in these sections is that you have a region on the ground and you have a surface, and those things are separate. So all of these questions are like this. You have a region on the ground, let's call it R, and that's what this is. This notation means all the x values between 0 and 2. This is called the Cartesian product notation for two sets, but it just means the pairs of numbers where the first number comes from the first set and the second number comes from the second set. So don't let that bother you. So collectively, the precise volume you would get between these things all together is defined to be the following. It's this. It's the double integral of r of x plus 2y squared dA. So we just want to talk about the area without actually computing it. That's what we write. When we write that, what we're saying is we have yet to decide how we're going to do the bounds. And by the end of chapter 15, we will have 3 ways to do the bounds. So this is just saying we haven't yet decided the order we're going to do it. This represents the area of the base, so to speak, and this represents the changing height. What we really mean by that is the volume, but how do you even define volume if it's not a rectangular shape? So just like in Math 124, we do the following. We break it up into subdivisions. So again, we're not going to do a lot of this, but I want to show you a little bit because I think it explains the notation a little bit. So right now I'm just going to break it into 2 columns and 2 rows. So just like in Math 125, you can find the width of 1 column and you can find the width of 1 row by using that same idea. Meaning the idea was this, b minus a over n. But for x, you're dividing up. So if you've forgotten this piece, the good news is you're not going to do very much with it, but there is one homework question. So delta x, oops, I miswrote there. This was 2. This is 1. That's 1. And that's 1. And delta y is 4 minus 0 over 2. That's 2. And then just like you did in Math 125, you label the tick marks. But if you start to label the tick marks, what all of these points are, you realize for each row there are 3 x's. And there are 3 rows. That leaves this thing we would call a double sum. That's where this is coming from. And for each one, what we're going to do is we're going to estimate the height. Now this says we're going to use upper right endpoints. So for each, there are now 4 boxes. And I'll show you visuals of this in a second. Maybe I'll call this 3, this 4. And over each one, I'm going to go up to the surface and I'm going to draw a rectangular box of that height. So I'm going to go up here and then draw a rectangular box. That's going to give me a terrible over approximation. Let me show you that because maybe it's a good time to do this. Here's this surface. And here is me starting to put boxes in. There they are. So we're going to find the volume of those 4 boxes. Like I said, it's going to be a terrible over approximation, but each one is going to be the area of the base, which we know, the area of the base, which we call dA. This is just to sort of get a sense of the notation. And it's practical. I mean, this is the way you would compute it. So the area of one of these bases is 2. 2 square feet, let's say. And then we're going to compute the height, but that's changing. So you would add up all 4 heights. 2, 3, 4. So you do the height at the first upper right endpoint. What would that be? It'd be 1, 2. Then you multiply times the area of the base. Then you would do the height at the second upper right endpoint, which is 2, 2. So I'm just labeling these points. They have to tell you which point you're using. And it did. So that's like going across 1 row. We basically did this, and then we're going to repeat for the second row. That's like the double sum. We're not going to do a lot with the full notation, but I wanted you to at least see it. So this point here, this is the upper right point when you're standing in here. And that's 1, 4, delta A. This should be delta A. And then lastly, we're going to have f of this corner point, which is 2, 4, delta A. And you just compute those, meaning you actually plug in a 1 and a 2 there, and you're going to get a number. And that would be the area of those 4 green rectangles. So plus 2 times 2 squared times the area, which is 2. Then you're going to have 2 plus 2 times 2 squared times the area, which is 2. And then you're going to have 1 plus 2 times 4 squared times 2. And then you're going to have 2 plus 2 times 4 squared times 2. I think it's like 196. It's in my notes. I realized I didn't pull those up. And it's a terrible over approximation. But that just gives you the idea of how we would approximate. You could do lower left endpoints, lower right. So what I did in this little animation is I made it so that I could add a lot more. Again, I'm spending too much time here, but here it is. So the more and more of these you put in, the more accurate it gets. There is 13 rows and 13 columns. It's going to get closer and closer to the volume. Okay, so that's the idea of that gives an official definition that always works, even if you can't do the iterated integrals. Just like in 125, if the function is above the ground, in this case the xy plane, it counts it as positive. If it's below, it counts it as negative. Notice we're just multiplying this times the area of the base. So just a few comments. A double integral is just like before a product. It's going to be the units of this times the units of the area on the ground. That's how we think about it. Okay, and this can be used to compute other things. So that's what you're going to play around with in 2 homework questions. All right, the actual theory of what we're going to do is we're going to, just like we did before, we're going to fix a variable. For example, we're going to fix x equals a number, 2, I don't know. The moment you fix that, then we can say, for a given x, what is the area? And that's what this is. The cross-sectional area at 2, or whatever it is, and then we add up the area. So again, just like in Math 125, you had, instead of an integral, you had like a disk or washer here, because that was the cross-sectional area. So this is a generalization of that. So when this is on the outside, in here you're treating x as if it's fixed, just like we did in our little entry task thing. And when you're here, we're treating y like it's fixed. The fact that either one of these gives you the value, as long as your function behaves normally, that's called Fubini's theorem. And you'd have to read up about some of the subtleties, but I already showed you some visuals of that. Okay, this is just for a rectangular region. In the next lecture, we'll talk about what if the region on the ground is more complicated. So I'm going to finish this with just 2 quick examples that I always do in class, and I have students try to visualize. So again, every one of these has a surface. The surface in this first example is z equals 5. The surface in the second example is z equals 2 minus x. And I have students try to visualize just to sort of get a feel for this. So what this is saying is I have a surface, and that surface is z equals 5 units up. I think this will give you a lot of understanding, I hope, of what's going on. So here's x, here's y, and I'm going to draw another one here. X, y, this is z. Darn head, you're getting in the way again. Ew, tiny. Okay, and then we're going to graph this. Z equals 2 minus x. If you were to graph that, when you plug in 0 for x, you get a 2. When you plug in 2 for x, you get a 0, and it looks like this in 2D, and then it extends out. You could call that a line cylinder, or more accurately, it's a plane. The region on the ground is all the x's from 0 to 2, and all the y's from 0 to 3. So there's the region on the ground. Again, that's what this is saying on the outside. This same thing, I think this is 2, and this is 3. So it's actually the same region on the ground. So one of the points of this problem is that the region on the ground is not enough to talk about the volume. You need both the region on the ground and the surface. So oftentimes what I'll have students do in these problems is try to guess what the volume is here, right? This is 2 by 3. And this is my belief that you should always do an example where you know the answer first and make sure it works out. So the volume of this should be 2 by 3 by 5, which is 30 cubic feet. And the volume of this would be, well, the area of the side is 2 by 2, because the height of this is 2. So the area of that triangle is 1/2 2 times 2, and then the length is 3. So I'm getting that this is 6 square feet, cubic feet. Okay, let's see if the double integral gets the same thing, and along the way, let's talk about some of the pieces. Okay, so this is saying we are going to compute the inside first, and when we're on the inside, x is the variable. So we're going to get 5x evaluated from 0 to 3 dy. We're going to plug this in, and we're going to get the integral from 0 to 3 of 15 dy. So now if you think about it, if you fix a given y here, we get that the cross-sectional area is 15. That's this piece here. This is 3. Y is 3? Yeah. 3. Am I labeling this right? 3 by 5. That area is 15. I don't know why my labeling doubted me for a second. So that's what this means, is cross-sectional area. Oh, that's what I did wrong. I need to be plugging in a 2. I get it now. I was like, this is not right. It's backwards. I apologize. I can't fix that like I would in class. There's evidence forever that I can't. I'm not smart. That wasn't hard to find. Okay, we should be fixing a y. That's what I was having trouble. The number wasn't coming out. That's 2 by 5. That's 10. And it's constant. Everywhere along the way, the cross sections are 10. And then you integrate. It's 10y from 0 to 3. It's 30. Hooray. This one, if you do the cross sections, let's see what happens. So we're integrating with respect to x. You're going to have 2x minus 1/2 x squared from 0 to 2 dy. And so you're going to have the integral from 0 to 3 of 4 minus 2 dy, which is the integral from 0 to 3 of 2 dy. Again, that represents the cross-sectional area. It represents this. And each one of those has area 2. We already figured that out. And then if you add those up, it's 2y from 0 to 3, and it's 6. Hooray. So I find those two examples to be quite informative, and that's what we're doing in general. Okay, I'm sure that video is too long, but let's just take a peek at the homework, and then I'll follow up with some more pointed examples. Again, you can go back and do any of those examples again, try them on your own, and then watch the lecture. But here's what the homework looks like. There's the Riemann sum problem I was talking about. Okay, so I believe what they mean here is that delta x is going to be 8 minus 2 over 3, which is 6 over which is 2. And delta y is 8 minus 4 over 2, which is also 2. And you're doing, so for each of these, this question, you're going to have something that looks like, let's see, x goes from 2 to 8, from 4 to 8. We're going to break it up here into 3 columns this way and 2 columns this way. This means this will be 6, this means this will be 4, and this will be 6. And we're going to use upper right point. So when it says upper right point, you're going to play this game. You're trying to estimate the double integral of xy dA, and you're going to one by one plug in those points to this thing and multiply times the area of the base. So you're going to have x times y times the area of the base, which is 2 times 2 times 4. And you're going to do it again for all 6 of them. So your job is to do that calculation for each one of these points. The first one would be 4 and a 6. The first thing here would be 4 and 6. And you keep going. The midpoint rule says do the exact same thing, but use the midpoint of each one. So the first midpoint would be 3, 5 for me. So instead of doing 4, 6, I would do 3, 5. Everything else will be the same. Okay, so that was just to sort of get you doing the notation, how you'd approximate. I think there's one here where they have you think about it, like what would happen if you were dealing with, that's part of a circle. This is a semicircle if you were going to draw a hemisphere. Boy, I can't say it. It says, what if you're trying to approximate that, some region under there? What can you say? Is it an upper estimate, a lower estimate? So that's more a conceptual thinking. you can ask me on the discussion board if you're stuck. And then it has you do some straight computations. So it would be nice to try to visualize. You can also compute. You can do it in either order, because we're talking about rectangular regions, and then you can go. This is kind of more of the same. You can just compute. So you can do the integral from 1 to 2. On the inside, you integrate y as if it's your only variable. Do remember, when you integrate a constant, you don't get 0. So if you integrate like 4, you get 4y. So the first step here is going to be 3x squared y squared, 3 because of the 1/2, minus 2xy, evaluated from y equals 0 to 3. And you're going to plug this in for y. And also you're going to plug in 0, and you're just going to keep going. 1 to 2. Let's see, that's going to be 4, so it's going to be 12x squared minus 4x dx, and then keep computing. In the homework, there's only one box. Sometimes when I print it in OneNote, it does that. That's kind of what these are. Okay, and that one's not too bad either. As soon as you get to about number 7, you're going to have to remember things like substitution. Actually, yeah, substitution there, substitution here, by parts. That's the game you're going to play. Substitution. So there's about 4 problems in a row that are going to require you to review more integration. And then there's a few problems that require you to set up, but I'll have a separate video about how you do setup problems. Okay, that's the idea.